Okay, this is a problem from Introduction to Quantum Mechanics, third edition by Griffiths. So, problem 1.3. Consider the Gaussian distribution of the distribution function rho of x equal to a e to the negative lambda quantity x minus a squared, where a, the capital A, small a, and lambda are positive real constants. Now, you're asked to find, to use equation 1.16 to determine A, and I will write equation 1.16 shortly. You are also asked to find for the expected expectancy. This is the expectancy value for x squared, and the sigma or the standard deviation. And we will not do the sketch of the graph because you can basically look for it. So let's try to write first the equation that is being referred to in the problem. So the equation is, you have to recall that the integral of all possible values from negative infinity to positive infinity of the distribution function rho of x multiplied by dx should be equal to 1. And if you can recall, this is your normalization condition. So we're going to use this one. If you can remember also, when we try to normalize, we look for the value of a. That's why the problem is looking for determine the value of a. So in this problem, we can simply write this one as like this. The integral of all possible values from negative infinity to positive infinity. Our rho is, our distribution function is a e to the negative lambda quantity x minus a squared dx, and that should be equal to 1. So from here, what we are going to do is to have some u substitution, or we let u be equal to x minus a. Because if you try to look into this one, this looks like a messy integral. So that's why we have to let some variable, change of variable to simplify it. That means to say the derivative of u will simply be dx because the derivative with respect to some constant will be just 0. So that's why we have established that the derivative of u is just equal to dx. And also, always remember this one, since you are changing variables, the limits should also be changed. So changing the limits. And it's very easy to do because you just have to write that when you set your x be equal to the negative infinity, the lower limit, what happens to the value of u? So u simply becomes, so from here, if this is negative infinity minus a constant, that would still be negative infinity. And when the value of x on the upper limit is positive infinity, you go back to your u is equal to x minus a, the one that you let earlier. And when this is positive infinity minus a constant, that won't affect the x, would still be positive infinity. So we can now re-express our integral. The lower bound, the lower limit is still negative infinity. The upper limit, as you can see here, is positive infinity. And then we write a e negative lambda. And you have to recall that we already let this term x minus a as u. So that means to say that will now be written as u squared. And then the dx also, this should also be changed. So we have understood earlier that dx is just equal to du. So that dx now will now be du. And also, it's a good thing we have also already changed the limits of this one. So always remember to change the limit when you change your variable. Sorry about that. So from there, we are trying, sorry, should be equal to 1. So from this point, what we're going to do is to check the integral. So what I mean by check this integral, notice that this is actually an integral from negative infinity to positive infinity, and we have this following theorem which will come in handy. So recall this one. If you have an integral from negative infinity to positive infinity of, say, f of x, and when your f of x is actually an even function, this tells you that that integral will just be like twice of the half. So when I say half, you start from 0 to positive infinity of the function of x. Sorry, it should be dx. Function of x dx. Now another is if we have an integral from negative infinity to positive infinity of, say, g of x dx. And when you try to evaluate g of x and understood or knew that that's an odd function, that integral will simply be equal to 0. So we're going to use this one to simplify our integral, because as you can observe, this is actually an integral from negative infinity to positive infinity. So we could actually use this one. Now, how do we check? So I'm just going to write it here. You check if even or odd. Now, how do we check that one? It's very simple. So we just write as a f of x is equal to a e negative lambda u squared. Okay. So let me just simplify first the integral. Sorry about that. Since a is a constant, we knew that we could take that out of the integral so that we will deal with a simpler integral. So what is left would be e to the negative lambda u squared du, that is equal to 1. Now, so that means to say that our f of x upon testing if it's odd or even would simply be this term here. Now, when we do the f of negative x, we get e to the negative lambda. This is just telling us that the u there will be changed to some variable. This should have been u, sorry, since we have changed. So f of u, f of negative u. So u squared, that means to say when we take the f of negative u, the u there will be replaced by negative u and then squared. Now notice that the f of negative u will give you e to the negative lambda, and negative of u squared will simply give you u squared. So what we're actually seeing here is that our f of u is simply equal to the f of negative u. Now when you notice or when you see this to be true, that means that your function is symmetric or even. So that means to say we're going to use this theorem number 1. It means to say that our integral here would be reduced to this form. This one will just be a, and then notice that this is an even function, so we use this. So we now have twice of the integral from 0 to the positive infinity of e to the negative lambda u squared du. Alright, so this is actually an easier integral because this term here is some Gaussian integral, and you have to recall this one also. Recall that if we have an integral from 0 to positive infinity of e to the negative a x squared dx, that is actually a Gaussian integral which will give you 1/2 of the square root of pi all over a. So this is like an integral which we should be familiar with because we will always meet this one. And if you notice in your integral here, you can actually see that this integral resembles this one in the sense that you got e, okay, e. You get negative here. Your lambda is just a, which is just any constant in this matter. Your u squared is just x squared du dx. So that means to say we can actually apply this one, and this is telling us that the entire thing here, forgot the equal to 1, the entire thing here, I'm referring to this integral, would be expressed in terms of this form. The only exception would be the a now is just lambda. So that means to say we have 2a, and then the entire integral would just be written as 1/2 square root of pi. And then our a is the constant, in this case this one here. So for our problem it's lambda. So you're just going to write here lambda. And then that's basically it. So it's equal to 1. Now we can further simplify this one. The 2 would cancel out, and that gives us a square root sorry, it should be, yeah, like that. A square root of pi all over lambda is equal to 1. Now we're looking for the value of a, so simply you can just multiply both sides of the equation by the square root of pi over lambda, and of course the right hand side would turn to 1, and then we have the value of a. Now a is simply the square root of pi all over lambda all over pi. So this is the value of a for your probability distribution function above. Okay, so that's the value of a. It should be lambda over pi. So we are now done with answering a. So let's proceed to find the expectancy value of your x squared, and then your standard deviation. So let's start with the expectancy value of of x. Sorry. So the expectancy value of x, if you can remember, is simply the integral of all possible values, so from negative infinity to positive infinity of x, multiplied by the probability distribution function rho of x dx. So that's basically the formula of getting the expectancy value. So if we're looking for the expectancy value, we have negative infinity to positive infinity x, and we knew earlier that our rho of x is just a to the ae to the negative lambda x minus a quantity squared dx. So we're going to evaluate this integral, but then again, the same with what we did earlier. I'm just going to write it here again. Earlier we let u, to simplify our calculation, be equal to x minus a. This implies that taking the derivative both sides would yield to du over dx. And another implication of this one is this means to say that the value of x is simply be equal to u plus a, because we're going to use this term here because of the fact that we have a factor of x here. So from our integral, it will continue to become negative infinity to positive infinity. As I've said, the value of x is simply given by the one that you let, u plus a. So this is going to be u plus a. And then we have a e to the negative lambda. And everything here, x minus a is just u. So you got u squared there. The same with what we did earlier, u squared. And then the dx, as you can see here, the dx is simply du, so that means to say we can just replace it by du. Also, as I've said earlier, we do the change of variables over here. So how do you do the change of variable? The same with what we did earlier. We just set the value of x at its lower limit and evaluate it with the new value of u. That's going to be negative infinity. Now when your x is positive infinity, referring to the upper limit, the value of your u here, when you substitute x as positive infinity, would be positive infinity. So that means to say that we still have the same limits of integration from negative infinity to positive infinity. Now what we're going to do next is simply a matter of distribution. So this term here, I'm going to distribute it to each of the term, respectively u and a. So what would happen to our integral would be integral from negative infinity to positive infinity of this is u a e negative lambda u squared du. And this is a property of integral that if you have a sum that's just equal to the integral of each of the terms. So the second term would be, if I'm going to distribute this term over plus a, so I have plus, and that will be a e to negative lambda u squared du. All right, so we have to remember something. This a here is a constant, so that can actually be taken out of the integral, which I will do later, but this u is a function of x, so you cannot take this out of the integral. So that means to say this is gonna be negative infinity to positive infinity of some u a e negative lambda u squared du, but the next integral can be written as a, as taken out of the integral because it's just a constant, And then we have ae negative lambda u squared du. Now what we're going to do next is to actually check for the symmetry, and we're going to use this trick in simplifying this one. We evaluate whether it's an odd function or even function or an odd function. So we're going to again evaluate the function. So odd, I'm going to write here, or even. So that's the question. And this one also. So we'll do the first term So I'm just going to write the f of u is the entire thing. That's u a e, and this is very apparent, u squared du. Now, if you take the f of negative u, that would give you negative u a e negative lambda. This is just negative u squared. But what f of negative u equals to is negative u a e negative lambda u squared. Now, if you try to compare f of u and f of negative u, you'll see this, that the f of u is simply equal to the negative of f of negative u. That means to say that they are not equal. So if that is the case, we know that this implies that it's an odd function. Okay, now we like this one because if you can recall, whenever you have an integral from negative infinity to positive infinity of some odd function, that would just be equal to 0. So that means to say this first term here would vanish. It will just be 0. And what remains is your second function over here. And I'm hoping you can just go back. This one is actually very the same with what we did earlier. This one here. And we knew it's an even function. So if it's an even function, we utilize this theorem. So that means to say it's just going to be twice of the half from 0 to this should be infinity. 0 to infinity of f of x dx. Right? So I think I don't have to show this to you, but I'm just going to tell you that this is going to be an even function. And when that's an even function, we apply the theorem. That's just going to be twice. And of course, we still have a constant a here, 2a. Integral from, and that will now be reduced from 0 to positive infinity of a e to the negative lambda u squared du. And by now, I'm hoping that you can see that I can further simplify this one by taking out the constant capital A, 0 to positive infinity. What is left is e to the negative lambda u squared du. And again, this integral over here should ring a bell. This is a Gaussian integral of this form. The integral from 0 to positive infinity of e to the negative a x squared dx, where a is just a constant with respect to x. And that integral is actually simply equal to 1/2 of the square root of pi all over a. So I want you to look very closely of this form, and I'm hoping you can realize that it is just this form. It's just that instead of x, you get u, dx, you get du, and instead of a, which is just any constant, you get lambda, which is also a constant with respect to u. So you can surely use this integral, and that is just be equal to 1/2 of the square root of pi over a. So what this is telling you is that you can simply have this. You now have 2a, and this entire integral would reduce to 1/2 of the square root of pi all over the constant lambda. Okay, so clearly we can simplify this one. The 2 on the numerator and the denominator would cancel out. So we now get a multiplied by the square root of pi all over lambda, and then multiplied by a. But you have to recall earlier, we actually have solved for the normalization constant a, and that is square root of square root of lambda over pi. So we can substitute that here. So a is the square root of pi over lambda. And this is looking promising because as you can see, if you're substituting pi all over lambda, sorry, lambda all over pi, and you multiply it by some pi all over lambda. That looks very good. And you do some a little bit of review in your algebra, so you can just, they both have the same indices here, that's 2. So this could be reduced like this. This could be taken into some single radicand. So pi all over lambda multiplied by a. And as you can see, this cancels out, and the square root of 1 is just 1. So the expectancy value of your x is just equal to a. Okay. Okay, it's not, I want a perfect square. Okay. The expectancy value of x is just a.